welcome back. How are you doing?
Thank you, teacher. I'm fine. Thank you.
Okay, cool. Um, Sasha, what are your plans for the week? You gonna do anything exciting?
Resting because as I said, I am on my vacation.
Mm-hmm.
So, learning, resting, going to the beach, to the
Okay,
river.
nice. That sounds good. Um, yeah. How often do you usually go to the river?
Uh, Not usually, maybe one time a month. But
Okay.
now I'm planning on going uh, uh, every second, or how to say, every second day, like day, not
Every
no,
other day.
every other day, yeah, because now I have time.
Nice. That's great. Um, and cool. Ksenia, how's it going?
Fine, everything's fine.
Nice. Welcome back.
Thank you.
And Ksenia, what'd you have for lunch today?
Lunch.
Mm-hmm.
It's potato with slice of meat, with tomato, bacon, cheese,
Okay. Tomato.
tomato, tomato.
Okay. So potato, tomato, slice of meat, cheese, bacon. Sounds actually really delicious. I'd put it all like on a sandwich. I think that sounds good. What kind of meat did you have?
I don't know. It's my husband's mother did it for us. I think it's beef, but I'm not
Okay.
sure.
Okay. Okay. Cool. Um, and yeah, maybe. Hmm. Ksenia, do you have any plans for the coming weekend?
No special plans. Maybe I need to renew my driver license, so possibly I'll go to post office. I don't know how to say, not post office.
The post office.
Post office, yeah, the post office to change my driver license.
Okay. Cool. I actually need to change my driver's license too soon. I don't know how I'm gonna do it. Um, yeah, it's not exciting.
Eh,
Um, yeah. Sasha, what about you? Maybe who do you generally go to the river with? Or who do you like to go to the river with?
With a couple of my friends.
Okay, cool. What do you guys do there?
Um, Sand bath and swimming, of course.
Sunbathe?
Sunbathe, yeah,
Okay, good.
and swimming.
Cool, cool, cool.
Some of people want like playing with ball, but I prefer just land sand.
Okay. Um, and Amp, I guess what about you? Do you have anything you're gonna do with the rest of your week for the weekend?
On Saturday, I am going to have a party with my friends from the cooking class, and on Sunday we are going to have a barbecue with my friends from my elementary school. Because on
Nice.
Monday is a day off.
Okay, perfect. I'll see you at the barbecue. Uh, perfect. That sounds delicious. I haven't had a barbecue in a long time.
Mm.
Um, cool. All right, and if it's just going to be the four of us, let's get started with today's class. It'll be a reading class. What if? Um, let's start with Ksenia. Can you read the question? Sorry, I want to get it up. Can you see that?
what if, yes, what if you released a submarine into Jupiter's atmosphere? Would it eventually reach a point where it would float? Could it navigate?
Good. And Sasha, what do you think?
It depends. Does it have any gravity?
Jupiter.
Yeah, because I don't know.
Yeah, Jupiter definitely has a pretty massive gravity. Jupiter's definitely got gravity.
And then I'm not sure about the question. Is it what the release a submarine into Jupiter's atmosphere? If
Okay.
it have a gravity, it's just
So
be lying on the surface, and that's it. Or maybe I don't understand something.
I guess if we look at Jupiter, this is Jupiter. And so the atmosphere is what you see pretty much. It's a gas giant, so it's all gas up until like once you get inside it really far, the gas kind of condenses into some sort of molten plasma, which is no longer gas because of the intense pressure of gravity. Does
So like would it be floating in gas?
Yeah, would it ever like get to a point where the gas was dense enough for the submarine to float?
It's hard to say. I don't know, but for some time, for some distance, it might be floating, but
Okay.
I'm not sure exactly if it's all the time would be
Yeah.
floating around.
Okay. Good answer. What do you think, Amp?
I don't know. It is impossible. I think that if there is water on it, if they are able to find um,
Definitely no
water,
water.
yeah, it
No, I don't think there's any water.
yeah. So I don't know how can they float just on air on the atmosphere.
Yeah, I guess that's the
Depends on
question.
depends on the weight, I think, of the submarine.
Hmm. Okay.
But yeah, I'm not sure.
Okay. Yeah. No, I don't. Okay. And Anna Carolina, how's it going?
Hi, teacher. Fine.
Nice. Sounds like somebody's playing the piano.
Yes.
Okay. Cool. Well, welcome to class, and let's get started with reading. And I guess we're with Amp. Can you read the first paragraph?
Nope. Jupiter's pressure, density, density and temperature curves are different from ours. At the point on Jupiter's atmosphere where the density is high enough for a submarine to float, the pressure is high enough to crush the submarine, which make it more dense. And the temperature is high enough to melt it, which makes it harder to drive.
Yeah, which makes it harder to drive. Good. And so, any questions here? Okay. And maybe Anna Carolina, can you read the comic or like the diagram?
Submarine phase diagram. Shipwreck, triple point, submarine, molten shipwreck, temperature, pressure.
Yeah, so shipwreck, submarine, and molten shipwreck. And this is the triple point where they all meet. So it's yeah. Anyways, good. Can you repeat shipwreck, actually? Shipwreck?
Shipwreck.
Good. And can you read this next sentence, Ana Carolina?
But there's another problem. Jupiter is a gas giant, but submarines, as you can figure out from etymology, go under water.
Good. Submarines.
Submarines.
Good. Senya, can you read the comic?
Submarine. Under, from air, meaning lava field on the moon, or female Horse.
Yeah, so kind of a joke. Ksenia, can you read the next paragraph?
Air and water are different. This seems straightforward enough, but they're also the same in a lot of ways. They're both fluids and some of the same rules apply to each. In some sense, when you look up at the sky, you're looking up from the bottom of a deep sea of air.
Good. And if you want to, does anybody have any questions here?
Teacher is maybe a mare from mare.
Mare? Yeah, it's a joke with like female horse. Yeah, so a mare is a female horse. I think mare is also like something on the moon where there's like tectonic activity. I'm not actually sure about that. But he's making a joke about marine. He's like trying to find the etymology of it. Okay. And any other questions? Okay. And this is the comic it's referring to. Let's have maybe Sasha, can you read the comic?
I like the sky.
Yeah.
Yeah. It's one of my favorite halves.
Yeah.
Halves like parts.
Halves, yeah. So like there's a half. So like one half is the earth and one half is the sky. Actually, there's another little thing. But anyways, that's the comic it's referring to. So if you look up at the sky, you're looking up at the bottom of a deep sea of air. And Sasha, can you read this next paragraph?
Things things float when they are less dense than the fluid around them. This works the same for balloons in air and boats in water. The late Terry Pratchett wrote a truly beautiful passage about this in the prologue to this book, Going Postal. He says that since water is in many respects a wetter form of air, and I can see.
Can you read this part?
No. Okay. Yes.
So,
Sounds reasonable enough to me.
yeah.
As ships sink, eventually they reach a point where the water was too dense to sink any further. This layer forms an underwater surface on which shipwrecks collect, drifting around beneath the waves but far above the seafloor.
Nice. Okay, you did a really nice job. Does anybody have any questions here? Okay. Amp, can you read, I guess the first three paragraphs?
It's calm there, dead calm. Some stricken ships have rigging, some even have sails. Many still have crew, tangled in the rigging or lashed to the wheel. But the voyages still continue, aimlessly with no harbor in sight, because there are currents under the ocean, and so that ships with their skeleton crews sail cities and between drowned mountains until rot and shipworms eat them away and they disintegrate.
Nice. Okay, let's look at rigging. Rigging.
Rigging.
And do voyages.
Voyages. No. Repeat again, please.
Voyages.
Voyages.
Jizz.
Voyages.
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 Aimlessly.
Aimlessly.
Good. Okay. And Anna Carolina, can you read those next three little parts?
From where to where? Okay, nice. Sometimes an anchor drops all the way to the dark, cold calmness of the abyssal plain and disturbs the stillness of centuries by throwing up a cloud of silt. I love that passage. It's also completely wrong. Ships sink all the way to the bottom. It's so long, teacher. Sir Terry knew this, as the rest of the passage makes clear, but he's describing how ships work on Discworld, not Earth. Air follows the ideal gas law. The more pressure you put on it, the smaller and denser it gets.
Good. Okay, yeah, that sounded really good. Um, so we're talking about a place that's not on Earth, so ships don't actually float on a super dense layer of water when they sink. Does anybody have any questions so far? And all right, good. And let's have Ksenia, can you read the next two paragraphs?
Water, on the other hand, is pretty much incompressible. When you dive into the ocean, the pressure increases as you go deeper, rising by 1 atmosphere every 10 meters or so, but the water density barely changes all the way down to the seafloor. Buoyancy depends on density, not pressure. There is a point in Jupiter's atmosphere where the pressure is equal to a little more than in Earth's atmosphere, which is the pressure a submarine is used to, but the air there is barely a tenth as dense as ours. A submarine in that layer would fall even faster than it would in the air on Earth.
Mm-hmm. Good. So changes.
Changes.
Good. And buoyancy.
Buoyancy. And what
Good.
does it mean?
Does anybody know what buoyancy means? Any ideas? So let's look at I'm
Floating?
trying to find like Go ahead.
Floating?
Yeah. I mean that's simply put. Buoyancy. Let's look at this. Um yeah. Sorry, hold on. Um I think this is a good picture of it. This is kind of an example of buoyancy. It's like the pressure that the water places on an object, like based on the displacement of it. So like the more water that an object displaces, the more buoyancy it has. Like the more buoyant force is imposed on the object. And if the object is much denser than the water, the buoyant force, which is the force of the displaced water, is not equal. Does that make sense?
So it's ability to drift in the water.
Yeah, the
Something
ability
like
to
that?
float in water, for sure,
Mm-hmm.
is
Okay.
buoyancy. So buoyancy depends on density, not pressure. Um, yeah, is kind of what it's saying. Any questions? Okay. And Sasha, can you read the comic?
This is your captain speaking. We're experiencing we're experiencing something.
Yeah. And
I don't get it.
so they're on Jupiter supposedly, and they're falling even faster than they would in the air on Earth. Um, and there's a quote, I don't think you guys can see it beneath my mouse, that says, "Not sure what's going on, but you should probably fasten your seatbelts," assuming that these things have seatbelts. Um, and Sasha, can you read this next paragraph?
Uh, To reach a depth where it could float in Jupiter, the submarine would have to go halfway to the center of the planet, where the intense pressure turns the air into metallic soup that's hotter than the surface of the sun. The pressure there would be so high that not only would the submarine be crushed, the substances that make it up would probably convert it into new and exciting forms. It's hard to create those kind of conditions in a lab, so we don't know a lot about how materials behave with that much pressure pushing down on them.
Good. That sounded good. Any questions here? I actually haven't even looked at metallic soup yet. So, yeah, metallic hydrogen is what it's going to be. Okay, any other questions? All right, and I don't. This one probably won't make sense to any of you guys, but Amp, can you read the comic?
Sun start getting head. None. Under pressure. Ice, ice, baby.
Yeah. Yeah. Anyways, bad joke. Anna, welcome to class. Anna, how's it going?
I'm fine, thank you. How about you?
I'm doing really well. Thanks for asking. Amp, can you explain to Anna what we're reading about?
We're reading about the possibility of that a submarine float in Jupiter.
Yeah.
The
Okay,
condition.
that's interesting.
Yeah. And Anna Carolina, what have we learned so far about the possibility of a submarine floating in Jupiter?
It would melt because of the high temperature, and the pressure near Jupiter could crush the submarine.
Hmm. Yeah, and it would not float.
Yeah,
Okay. Amp, can you read this first paragraph?
Okay. In the sea, on the other hand, the density of the fluid stays relatively constant. That means the submarine can find its appropriate pressure range and float there. In other words, submarines only work because water doesn't follow the ideal gas law.
Good. What was the ideal gas law again, Amp?
The ideal gas law,
What was it? What's the ideal gas law?
I don't know.
Does anybody remember? Hmm. Do. Amp, can you read that?
The more pressure you put on it, the smaller and denser it gets.
Yeah. Water doesn't follow that. Water is pretty much always the same density. Good. Appropriate
Appropriate
and range.
range.
Good. Anna Carolina, can you read the next paragraph?
but there's one more twist. Water sort of does obey the ideal gas law. The equations governing water under normal pressure are similar to the equation for a gas under about 20,000 atmospheres of pressure. In a sense, this is why water seems incomprehensible,
Nice.
incompressible to us. It behaves as if it is already compressed so much that an extra atmosphere or two hardly makes a difference.
Good. Okay. Does anybody have any questions here? Anna, can you explain what's happening? What's this saying? Anna Carolina? Sorry. Anna Carolina, can you explain what this is saying?
Okay, I thought you
Yeah,
were
I know. Yeah, sorry.
okay. Um, okay, there is something else that is unexpected because water oh my gosh, it's difficult. Um, don't she, don't be behave like an ideal gas. Um, my gosh,
It's really tricky.
totally.
So water does behave like a gas, sort of. When gas,
Okay, so water does behave like a gas.
sort
Uh,
of.
however, um, it, um, I'm sorry, I'm not understanding.
Okay. Um, who can explain this paragraph? Does anybody think they can explain it? Anybody? All right. So they're saying pretty much before this, we've been saying water doesn't follow the ideal gas law. That like the more pressure you put on water, the more it compresses. Water is pretty much always at the same density where gas changes. Water kind of does obey the ideal gas law in that if you have a gas that's under a ton of pressure, it will act the same way that water does. So water under normal pressure acts the same as gas under 20,000 atmospheres of pressure, which is a lot of pressure. And that's why water seems incompressible to us. It's already compressed so much that a little bit of extra pressure doesn't compress it. Does that make sense to everybody?
Joshua, and in incompressible, it means that we can't burn it, or no?
Incompressible means that we can't squish it together anymore.
Screen.
The atoms don't compress. Whereas with a gas, you can make it tighter and tighter and
Yes,
tighter and tighter.
yes, it's clear.
Water, yeah, water is just the same. It's like you're on the stage and you just rattle off your line. All right, Anna, can you read these next two paragraphs?
Yes. So in some ways, water and air are similar than they seem, but in the ways that matter for a submarine, they really are different. Which of course bring us back to why it's called a submarine. It operates under a mare. A vehicle designed to operate beneath a sea of air would be called a souvenir.
Submarine.
Submarine.
And can you read that part?
The gas in gas giant is from the Greek word for what? Void.
Void.
Void. So maybe a weasel that travels through a gas giant atmosphere would be a
A
cow.
chaoscape?
Oh my god. Cowscape? Cowscape.
Yeah, cowscape? I don't really know. I'm not sure how to pronounce my Greek. Can you repeat giant?
Giant.
Giant. And yeah, void.
Void. Yeah.
hmm And Xenia, can you read the last part?
Which, come to think of it, it's a perfectly good description of a car.
Yeah, so this is a submarine. Good. And does anybody have any questions here? Okay. So I guess basically no submarines on Jupiter. I want to get to the archive here. And so we finished that pretty early. Have you guys done the glass half empty yet? Have you read that one? Probably Amp
No,
has.
No.
I didn't.
Okay,
I don't
Amp
think so.
did. Okay, that's a funny one. We can try that. And let's have Ksenia. Can you read the question again?
What if a glass of water was all of a sudden literally half empty?
Good. And Sasha, what do you think would happen?
What if glass? What does it mean all of a sudden?
Like instantly, like in a snap of a finger, if it was half empty. Yeah.
I thought it's magic
It would be magic.
or
This is maybe
aliens in my room.
it's a little bit tricky. Let's have Sasha, can you read the first two paragraphs?
Okay. The pessimist is probably more right about how it turns out than the optimist. When people say glass half empty, they usually mean something like glass containing equal parts water and air.
Yeah. And maybe let's have Sasha, can you read the comic?
Okay. Optimist. Oh, water, I bet we'll get to drink it. Pessimist. Drinking fluids postpone death but doesn't avert it.
Good. Um, let's have Amp, can you read this paragraph?
Traditionally, the optimist sees the glass as half full, while the pessimist sees it as half empty. This has spawned a zillion joke variants. Example: the engineer sees a glass that's twice as big as it needs to be. The surrealist sees a giraffe eating a necktie, etc.
Good. Um, avert, yeah, is like prevent to. Um, avert death, prevent it, avoid it. Yeah, probably prevent is a little bit closer. Similar enough. Does anybody have any questions so far?
Yeah, I have one question
Hmm.
regarding necktie.
Yeah.
What's that?
Necktie. Does anybody? Well, this is a necktie.
Okay, okay, okay.
Yeah. So
Okay, so
why would you?
it's just a tie. Okay, okay, just a tie.
Yeah.
Okay.
Yeah.
Mhm.
Well, yes. Sorry. Yeah. Anna Carolina, we would. Um. Yeah. Avert dying, avert death. We like we avert things. So like we avert disaster or avert death. So you generally use a noun after it. You could use the gerund after it. Hmm. Yeah, like avert having to go to. Yeah, you'd use the gerund after it if you were going to use a gerund. I think generally nouns work better, but if you're going to use a verb, use the gerund. Okay. And right. Anna Carolina, can you read the next two paragraphs?
But what if the empty half of the glass were actually empty? A vacuum? Even a vacuum, ar- argu- arguably, arguably, isn't it truly empty? But that's a question for quantum semantics. I don't know this word. The vacuum would definitely not last long, but exactly what happens depends on a key question that nobody usually bothers to ask. Which half is empty?
Good. Okay, let's look at arguably.
Arguably. Arguably.
Semantics.
Sem-
Semantics.
sem- sem- Semantics. Teacher, what does semantics mean?
Good. Really good question. Does anybody have any ideas what semantics means?
It's science?
It's a science?
No? It's
Yeah,
kind of
it's
science.
like it's the science of linguistics, like the science of how words have meaning, kind of. So like semantics is generally if you claim it's like semantics, it's like everybody knows what I mean. The only people who would argue are people who are like way too obsessed with the actual meaning of words and not like understanding them. So yeah, semantics is the literal interpretation of words, um, like the science of interpreting words and meaning. Does that make sense?
Yep.
Okay, good. So quantum semantics, it's like, what is a vacuum? And like, what is empty? What is truly empty? So those are all like semantic questions because you're questioning the meaning of words. Anyways, any other questions? All right. And Anna, can you read this paragraph and then the comic? Anna?
Yes, for our scenario, we'll manage 3 different half-empty glasses and follow what happens to them microsecond by microsecond.
And the comic?
Okay, water, vacuum, air, water, vacuum, water.
Good. And can you read this next little paragraph too?
Yeah. In the middle is the traditional air-water glass. On the right is a glass like a traditional one, except the air is replaced by a vacuum. The glass on the left is half full of water and half empty, but it's the bottom half that's empty.
Nice. And Ksenia, can you read the next sentence?
We'll imagine the vacuums appear at time t equal 0.
Yeah.
Time equals 0.
Time equals 0. Good. And next sentence, Ksenia?
For the first handful of microseconds nothing happens. On this time scale even the air molecules are nearly stationary.
Good. And so this is what it looks like at 2 microseconds. Any questions so far? Okay. And Sasha, can you read the next paragraph?
For the most part, air molecules jiggle around at speeds of a few hundred meters per second, but at any given time, some happen to be moving faster than others. The fastest few are moving at over 1000 meters per second. These are the first to drift into the vacuum in the glass on the right.
Good. Questions? All right, Amp, the next paragraph.
Okay. The vacuum on the left is surrounded by barriers, so air molecules can easily get in. The water, being a liquid, doesn't expand to fill the vacuum in the same way air does. However, in the vacuum of the glasses, it does start to boil, slowly shedding water vapor into the empty space.
Good. That sounded great. Any questions?
I forgot the meaning of shedding.
Shedding. Okay, does anybody know what shedding means? cats shed and dogs shed. What's that mean? Nobody. Okay. So shedding is like when you lose things. So if a cat is shedding, it's like when you pet it, its fur comes off. That means it's shedding. It's letting go of things. So the water in this case is shedding water vapor. It's like letting go of water molecules in like the form of water vapor into the empty space. Um, and this is kind of what it looks like. And Anna Carolina, can you read the next paragraph?
While the water on the surface in both glasses starts to boil away, in the glass on the right, the air rushing in stops it before it really gets going. The glass on the left continues to fill with a very faint mist of water vapor.
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 Good. Nice. And this is what it will look like. And let's have Anna. Can you read the next paragraph?
After a few hundred microseconds, the air rushing into the glass on the right fills the vacuum completely and runs into the surface of the water, sending a pressure wave through the liquid. The sides of the glass bulge slightly, but they contain the pressure and do not break. A shock wave reverberates through the water and back into the air, joining the turbulence already there.
Yeah. Maybe turbulence?
Turbulence.
Good. Any questions here?
Reverberates.
Reverberates. Does anybody know what reverberates means?
And also, sorry, bulge.
Okay. Bulge and reverberates. Does anybody know what reverberates means first?
I don't know, it's like a boil.
Not boil. Reverberate is more like echo or like vibrate in with a shock. So like a drrrr kind of sound. If you hit a gong, it will reverberate. So it's like, yeah, does that make sense, guys? Nobody?
Yes.
Okay, yeah. So again, it's like kind of echoing or bouncing off of something.
So it hit back.
Yeah.
For example, if you hit something, it hit your back. Something like that. But it's not
Sort of.
yes.
It's like a shockwave reverberates through the water. Like it fills up the water. The shockwave like goes into the water, then like kind of bounces around in there. It's like it begins to vibrate in the water. Echo is more like hit back. Reverberate is like more like, you know, fill with vibration. Or like it also bounces off of it.
Like creating waves or something like that.
Yeah. So it would create waves for sure.
Okay. And
And
I'm sorry, but I also, gosh, I don't know rams
okay,
either.
that's okay. Don't be sorry again at all. This is good. These are words that most people probably don't know either. Bulge. Does anybody know what bulge means?
Yes, like something protrude.
Mm-hmm.
Like if you have in your pocket maybe apple and it bulge
Yeah,
in your t-shirt.
an apple would bulge out of your pocket for sure. Bulge is like get slightly bigger with two G's, not one G, like a protrude. And ram. Does anybody know what ram means?
Run into or something
Mm-hmm.
like that.
Yeah, exactly. And so it actually comes from rams, which are an animal, when they ram into each other. So the verb comes from them. So these are rams, and they are ramming each other. Does that make sense, Ana Carolina?
Yes, now it does. Thank you.
Cool. And where were we? Ksenia. Ksenia, can you read the next paragraph?
The shockwave from the vacuum collapse takes about a millisecond to spread out through the other two glasses. The glass and water both flake slightly as the wave passes through them. In a few more milliseconds it reaches the human's ear as a loud bang.
Mm-hmm. That sounded good. And Ksenia, can you read the next sentence?
Around this time the glass on the left starts to visibly lift into the air.
Yeah, which is ridiculous. Sasha, can you read the next paragraph?
The air pressure is trying to squeeze the glass and water together. This is the force we think of as suction. The vacuum on the right didn't last long enough for the suction to lift the glass, but since air can get into the vacuum on the left, the glass and the water begin to slide towards each other.
Good. Any questions?
Suction.
Sorry?
Suction. Yeah.
Suction is like the force that lifts water through a straw.
It's like suck, but this is a noun.
Mm-hmm. Yeah.
The force that sucks.
Yes. Exactly.
Okay. Thank you.
Any other questions? Okay. And Amp, can you read the next paragraph?
The boiling water has filled the vacuum with a very small amount of water vapor. As the space gets smaller, the buildup of water vapor slowly increases the pressure on the water's surface. Eventually, this will slow the boiling, just like higher air pressure would.
Yeah. Okay. And any questions here? This is kind of tricky.
Built up.
The build-up, it's like the slow increase. The build-up. Yeah. The increase or the build-up of water pressure slowly increases the pressure on the water's surface. Eventually, this will slow the boiling, just like higher air pressure would. Okay. And let's go here. Ana Carolina, can you read this next paragraph?
However, the glass and water are now moving too fast for the vapor building. Sorry. However, the glass and water are now moving too fast for the vapor buildup to matter. Less than 10 milliseconds after the clock started, they are flying towards each other at several meters per second, without a cushion of air between them, only a few wisps of vapor. The, the water smacks into the bottom of the glass like a hammer.
Okay. Hammer.
Hammer.
Toward.
Torch.
They're flying toward each other several meters per second. Good. Any questions here? Okay. And
Sorry, Joshua.
yeah,
Wisps.
wisps.
Yes.
Does anybody know what a wisp is?
No.
Okay. So we can use wispy to describe clouds, especially, shoot. Oh man. Okay, let's look at this. So these are wispy clouds. They're like really thin, unsubstantial. Those are all wisps. So something that's thin and unsubstantial is a wisp. Does that make sense?
Yes, thank you.
Okay. Other questions? Okay. And Anna, can you read the next paragraph?
Water is very nearly incompressible, so the impact isn't spread out. It comes as a single sharp shock. The momentary force on the glass is immense, and it breaks.
Good. And water is very nearly incompressible. We've already discovered that in the last one. Yeah. And can anybody tell me why water is not nearly, or why it's not compressible?
May I?
Yeah.
Because it is already too much compressed, as
Yeah.
you explained,
Yeah.
right?
It's already too compressed. Yeah. So it doesn't follow the ideal gas law. Yeah. But good. Really nicely done. Good reading too, Anna. Um, and yeah, good answer, Anna Carolina. Ksenia, what about, can you read the next paragraph?
This water, yes,
Mm-hmm.
this water hammer effect, which is also responsible for the clunk you sometimes hear in old plumbing when you turn off the faucet, can be seen in the well-known party trick, recorded on Mythbusters analyses in physics classes and demonstrated in countless student dorms, of smacking the top of a glass bottle to blow out the bottom.
Yeah. Okay. I think that sounded good. Any questions?
Yes, I'm sorry. A clunk.
It's like clunk. It's onomatopoeia.
Okay.
Yeah. Any other questions?
Yes, my
Yeah.
gosh. Of the faucet.
Faucet. It's the hmm,
You think?
llave in Spanish. The sink. Yeah. The sink is like hmm,
The
the
top,
sink is
the knob.
the tub. The faucet is the thing that the water comes out of. So this is a faucet. Hope I'm sure that makes sense. Any other questions? Okay. And Sasha, can you read the next paragraph?
When the bottle is struck, it's pushed suddenly downward. The liquid inside doesn't respond to this suction, air pressure, right away, much like in our scenario, and gap briefly opens up. It is a small vacuum, a few fraction of an inch thick, but when it closes, the snap breaks the bottom of the bottle.
Yeah. Okay. And so that's kind of describing when somebody is smacking the top of a glass bottle to blow out the bottom. This is a paragraph that describes kind of what happens. There's like a small vacuum that opens up at the bottom, and then the water breaks the bottom. Amp, can you read the next part?
In our situation, the forces would be more than enough to destroy even the heaviest drinking glasses.
Yeah. And then situation.
Situation.
Mm-hmm. And can you read the next paragraph, Amp?
The bottom is carried downward by the water and thunks against the table. The water splashes around it, spraying droplets and glass shards in all directions.
Good. Um, and let's have Anna Carolina, can you read the next sentence?
Meanwhile, the detached upper portion of the glass continues to rise.
Good. And can you read the comic too?
Cool.
Uh-oh.
Uh-oh.
Yeah. And can you read the next part, Anna Carolina?
After a after half a second, the observers, hearing a pop, have begun to flinch, their heads lift involuntarily to follow the rising movement. Oh my gosh, the rising movement of the glass.
Good. Good correction. Rising movement of the glass. And Anna, can you read the next sentence?
The glass has just enough feet to bang against the ceiling, breaking into fragments,
And the next one?
which the momentum now spent return to the table.
Momentum.
Momentum.
Nice. And can you read the comic?
To be honest, I can't see it. It should go upper. Sorry.
The comic? Can you read the comic?
Okay. Hey, a free glass. Ah.
Yeah, so this is the optimist and this is the pessimist, which I think is hilarious. All right, Sasha, can you read the next sentence?
The lesson: if the optimist says the glass is half full and the pessimist says the glass is half empty, the physics ducks.
The physicist.
Physicist ducks.
Good. Um, okay, ducks is to drop below something. If you duck, you get down. So if like a baseball is coming at your head, um, someone will say duck. So it's like get down. Yeah, not the duck. So person, duck. That's not um, person ducking. Yeah, so this is somebody who's ducking. Um, that's what it means. So yeah, it's like to avoid, but like to get down in order to avoid.
Teacher, what about
Yes.
funks?
Thunk. It's again onomatopoeia. Thunk.
Ah, thank you.
Any other question? Okay. Yeah, thanks for coming in. Hopefully you enjoyed this. Yeah, it's about out of time, but have a really good day. Hopefully I'll see you guys again soon. And yeah.
Thanks, teacher. Take care. See ya.
Yeah.